So we talked about how DNA can become RNA, can become protein, but we didn't actually understand how the sequence of DNA and RNA can be translated into the sequence of amino acids. So I'm showing right here on the screen a sequence of 21 nucleotides. The following sequence is RNA because, as you can see, we have uracil instead of thymine inside the sequence. Now, RNA can be divided into a group of 3 nucleotides. Every 3 nucleotides, we will have something called a codon. And each codon, which is the sequence of 3 nucleotides, will be translated and read by different structures we have inside a cell into a one amino acid. So this one will be amino acid, this one will be the second amino acid, this one will be amino acid, this one, this one, this one, and this one. So every 3 nucleotides, we will have one amino acid. Now, the same sequence, the same codon, will always code for exactly the specific amino acid. So, in nature, we have 64 codons. And we have around 20 amino acids. So the following chart is just something called the codon chart. And it looks a bit complex, but it's pretty straightforward. So you have a specific sequence, in our case it's DNA. As you can see, we have T, we have thymine, of the sequence that we need in order to have a specific amino acid. So for example, if we have AUG, it will code for a specific amino acid. If we have CUU, it will code for a specific amino acid. However, because we have more codons possibilities than amino acids, you will have multiple codons for a single amino acid. For example, for leucine, we have 4 possible codons. For valine, for example, we have also 4 possible codons. This was a way of nature to prevent the damage of mutation. So in the future, when we study mutation, we will realize that mutation is when you have a damage to the DNA or RNA and a change to the sequence of nucleotide. Once you change the sequence of nucleotide, you might change the codons and you might change the amino acid that is going to be produced in the future protein. While we can buffer this fact and we can buffer this damage by having multiple codons for the same single amino acid. So for example, if I will even have a mutation over here in the 3rd nucleotide of the codon that creates leucine, even if I will change the 3rd nucleotide to something else, it will be still the codon for leucine. Therefore, a mutation to the 3rd nucleotide inside the codon of leucine won't cause any damage and change to the future protein. So in the future videos, you're going to see how the process of translation of the following RNA actually occurs. But for now, just remember that you have groups of 3 nucleotides in RNA, and each group will give you 1, or in our case, more, depends because you have multiple codons for some amino acids, to 1 amino acid. We will also learn that you have a sequence of codon that called the stop and start codons. For example, AUG is an example to a start codon. It codes for an amino acid, but it also codes to the start of the translation. It signals the future ribosome, which is the structure that is going to help us in the translation, where to start from. While we also have multiple stop codons. Stop codons will signal the ribosome and show the ribosome that we can terminate the translation and the structure and the build of the future sequence of amino acids. I hope this video made sense, and I will see you next time.